Assalamu alaikum, ladies and gentlemen. Welcome back to another live stream. It's been quite a while since I actually live streamed. Alright, let me share the stream. Please join my Discord server. You can find the link down in the description below. Alright, live. Alrighty. There we go. Perfecto. And hello Luminary, welcome back to the live stream. How is it going, man? Long time. Alright, let's see. Let's grab first of all the chat. Can you please confirm if the stream quality is fine? Because I actually have reset my computer and even changed my graphics card, so though I'm not really using my graphics card for the live streaming. I'm using just my CPU because, like, when you're messing up with Vulkan, it could mess up my stream basically. And like, if I do something wrong with Vulkan, I could crash my live stream. So I didn't do that. Although I'm slowing down my compilation time by stealing work from my CPU through, you know, encoding in software, but well, that was a dilemma that I had to choose between either risking my stream going corrupt because of Vulkan or just sacrificing compile time. So I decided to sacrifice compile time. And hello Marty Flowers, welcome back to the live stream. How's it going, man? Alright, so I guess let's get straight into it. And then while the thing is building, we could talk more about the plan of today's live stream. So yeah, alright, perfect. Okay, let's start a new project. Let's go, new project. And by the way, if you guys have any questions, please let me know. Alright, so C++ executable. I guess let's go with C++23. I don't know what you call it. Say VK Volcanic, I guess. Alright, fine. Or Kodotaku Volcanic. Alright, that's good. And let's actually create this thing. And let's go. Alright, let's grab this thing here. I'm just gonna configure first some settings real quick, which is so Visual Studio, of course, we're gonna be using MSVC, Ninja generator, though that doesn't really matter that much. And of course, as always, the save actions on save. Oh, oops, what the heck? Hold on, save actions on save. I'm quite sleepy, so hopefully that wouldn't interfere with my performance in this live stream. But anyways, we're having a late night stream. Oh yeah, let's go. Nacho El Carto, welcome to the live stream. You seems new here. You seem like you're new here. Alright, so almost forgot my English language grammar there, but yeah. Anyways, let's see where we at. Okay, so the actions on save, perfect. Anything else that we want? Oh yeah, I wanted to show you also my, if you're using C-Line like me, then my IDE, if you're curious about my plugins, I'm actually using Copilot and Inspection Lens. This one is very freaking useful though. It shows you the errors inline instead of having to hover over the error and stuff like that. And hello, Gilad Seraphim. Welcome to the live stream. It seems like we have 2 new people here. Alright, that's cool. Alright, let's get going, I guess. Let's get going. Yeah, let's get going. CMake was a hell for me when I just started, but now I actually enjoy it. Though it's still a hell for me when I see some really experts in this field and still write in very clunky CMake files. But anyways, let's get going. First of all, we're gonna use CPM, CMake Package Manager, CPM. Oh boy, okay. Well, not that CPM. Hold on a second. So CPM, oh my God, hold on. CPM CMake. All right, long live bash scripts. Long live bash scripts, yeah. Let's see. What the heck is going on here? Bro, come on, just give me the regular search, please. Okay, so CPM CMake. Alright, so this is what we need here. There we go. I'm gonna go down here, or you could check out also my dedicated CMake tutorial. You could also have a lot of information there, but for now I'm just gonna do like, I'd like to keep this tutorial a bit independent, but anyways, let's see what we got. So there's some examples there, and let's go to the wiki. I think not this one. Oh boy, where is it? Let's see. Add in CPM. There we go. Here we go. Let's just copy this file thing here, so it would download that CPM version for us, basically. There we go. And so right now we have a package manager. Perfect. Let's go straight into SDL. So we're basically going to add CPM add package. Well, it's SDL CPM add package. All right. And no, that's not what I wanted. Let's see. There we go. Perfect. I do need the latest commit. So SDL GitHub. There we go. So I'm going to take this latest commit, and I do this so anybody who actually clones this project and try to build it would be using the same exact commit as me. So there's no difference there, basically. Oh boy, failed to clone repository. Why? Oh, it's wrong name. Oh boy, GitHub Copilot. Okay, so I just fixed that. Now it should work. And after that, we also need like a set libs array. And then we're basically gonna add to that array SDL3, SDL3. And then finally, we're gonna link those libraries. So code attack, volcanic libs. Probably we're gonna need private here though. Okay, and let's just wait for this to clone the SDL project, and then it would basically link it. Just as simple as that, nothing crazy. So this is basically just an array. We would keep on adding the target names to it of the libraries, and then finally at the end of here we're gonna basically link all those libraries in the array into our executable here. Though our executable could also be called project, well, should be like this, yeah. Could be called project name. There we go. Alrighty. And let's just build this. Okay, as you can see, it's actually already built in SDL right now. So the only thing you need to make this work, only CMake and Git. That's all you need for now. Alrighty, perfect. Alright, let's get into it. So first, we're gonna include SDL, SDL3, SDL.h. And we're gonna create a simple window. Well, actually before that, let's make a little class. I'm not gonna go crazy on the OOP stuff. I'm gonna have one class for everything, because one of the mistakes that I've done as a beginner myself is that I've gone crazy on the abstractions, which really slowed me down, frustrated me. You really shouldn't do that. You only need to abstract when you actually really need the abstraction. Then you have to think about that. For now, let's go with class. I'm gonna call this app. Alrighty, and we're gonna have a constructor. Of course, a public constructor. I'm gonna have a destructor. You could put this into its own file, but I'm not gonna bother, honestly. And we're gonna have two functions. We're gonna have void init and void run. And as you're gonna see in a second, I'm only using this class just for organizational purposes. It would become apparent as I go, but nothing really OOP, you know. But anyways, so init and run. That's all we need for now. Let's create an app here, app class, and then we're gonna init the application and then we're gonna run it. As simple as that. Pretty much. Okay. So here we're gonna initialize SDL. Another thing is that I'm not gonna go crazy on the error handling. A lot of things doesn't, like, especially this is a beginner tutorial, don't really have to bother that much with the error handling, you know, most of the time. And a lot of these functions rarely fail, you know, so why really bother? Anyways, SDL init. Though for Vulkan, we're going to be using the Vulkan RAII, so like the C++ kind of wrapper, which would handle errors for us using exceptions. Though even without that, we're going to be using a tool called the Vulkan configurator in the Vulkan SDK. And like, you don't really need the Vulkan SDK. You only need it for the headers and for the debugging tools. For the headers, I'm actually gonna be downloading it and setting it up in the CMake itself. So to actually build a project, you don't need the SDK, but you do need the SDK just to get the debugging tools and like the compilers, etc. Though actually for the shaders, usually we would just like compile the shaders offline, but hopefully I would explore with you guys how to actually compile them at runtime using GLSL-lang library. That would be really fun. But anyways, you're just gonna click on the installer, click install next, and there you go. You're gonna have all the SDK tools here in your disk. Vulkan SDK, there we go. And here if you go to bin, you're gonna find all the actual tools that comes with it. Like this SPIRV tools right here are for shaders, for example. Though we're not gonna be using them. The only thing that is very useful here is VkConfig. This guy right here, oh boy, not that one. Let's just Vulkan configurator, there we go. Also, another one you could try is vkcube. This one just to make sure that your Vulkan stuff is working properly. If this works properly, then you're good. Like your Vulkan driver is actually perfectly functional. So other than that, the other tool we're gonna be using is for debugging. Let's see, the VulkanCapsViewer. This one is also very useful. Device can be uploaded to the database. Interesting. Sure, why not? Let's upload it to the database. Kodoteco. Submitted in a live stream. Okay, there we go. Cool. I finally got my hands on an RTX device. It's an entry-level RTX, but that's the best I could with my HP built computer for now. And my PSU, I didn't want to upgrade my PSU, especially that my local GPUs and stuff like that and like PC parts are very, very expensive, and also there's not a lot of options, so that's the best I could have done. But at least right now I have access to RTX capabilities. But yeah, anyways, what's we gonna do next? So here you're gonna find the extensions of Vulkan, which I'm gonna explain later on. You can find the queue families, the memory surface. So basically all the properties of your GPUs. If you have multiple GPUs, you could actually access them here. Other than that, you're pretty much good to go. All right. So these are the two tools. The third tool is RenderDoc. This one, you really need it as a graphics debug. Like, this is usually used by expert graphics programmers to debug their applications or engines or whatever. And but I really think that beginners would actually also benefit from this a lot by really checking out how things work under the hood through this debugging tool. So you're just going to go to RenderDoc, install this guy too, and you should be good to go. This is how it looks like, though I'm going to be actually showing you how you could use this tool as we go. But yeah. Anyways, other than that, what we gonna do next? Let's see. So we got SDL running, so SDL init, and now we also gonna do SDL Vulkan. So let's include SDL Vulkan here, SDL3, SDL Vulkan.h. There we go, and we're gonna say SDL Vulkan. So here's the SDL Vulkan functions that SDL gives us for cross-platform support. What we're gonna need is Lloyd library. So basically we want to Lloyd the Vulkan DLL, right? Or SO in Linux or whatever, depending on the platform. We're just gonna say null PTR. This is basically the custom path to the DLL. But in our case, we're just gonna say null PTR to, like, we're basically telling SDL to mind its own business and find out what it is in a cross-platform way. Of course, by the way, these two functions could fail. So like this one, true on success and false on failure. If you want to get the error message, then you just say SDL get error. And then here SDL Vulkan Lloyd library, true on success or false on failure. All right. I didn't want to clutter the code with the error handling, so it's very clear. If you want to go later on, check out the repo and read yourself all the steps that it takes to create a Vulkan application. It's going to be very clear for you. Anyways, now let's go here to the deconstructor and we're going to say SDL quit, too simply. And there we go. So right now let's actually run this and make sure nothing is problematic. Oh yeah, our first system error. The code execution cannot proceed because SDL3.dll was not found. Reinstalling the program may fix the problem. Now to fix this problem is you're just gonna add this like variable, CMake variable, to make sure that your DLL is in the same path as your binary. Otherwise it wouldn't find it and it would give you that error. Intel Graphics Analyzer something is also good and similar tool, especially for Intel. Yeah, that's true. So there is other debuggers. So like RenderDoc that I mentioned is a cross-platform debugging tool for graphics applications. But there's also custom debuggers like Nacho have mentioned. For example, Intel Graphics have their own Intel Graphics Analyzer, I think. I never really heard of it, but it's probably there. For NVIDIA, in my case, it's going to be Insight. And for AMD, I think they also have their own tool and so on. But anyway, so here we got the output directory. Let's see, archive output runtime output directory. You're gonna set this to CMake binary there /bin, and this would make sure that the DLL is in the same path as your binary, so you wouldn't have that error anymore. And there you go, boom, exit code 0, which means it's perfect. If you don't want, so like this way, the default is that SDL would be dynamically linked, which means that your application, if you look into bin here, here's my application, my exe, but there's also this DLL. So like if you want to export your application to the client, you have to make sure to take this code, like your exe, but also the DLL with it. If you don't want that, if you want to like statically link it, then what you have to do is set CMake variable. I think it's called build shared. Hold on. By the way, you're gonna notice that a lot of things I don't actually remember it, and you don't really need to. I only remember the things that I use a lot, and that's how it should be, because there's just a lot of information, especially when it comes to APIs like Vulkan, that you can't remember. Like You just have to go with the search engines and so on. But yeah. All right, so here we got the cache variables. So the cache, here's a lot of variables from all sorts of libraries. For example, SDL CMake file have their own variables for CMake that toggle all sorts of stuff. Like if you don't need SDL audio, you could actually disable this and it wouldn't get included into your project as part of SDL, which means your executable would actually be way smaller. All right, so there's a lot of things here. For SDL, what else? I think there's another variable called, hold on, can't find it. Let me just search for it, in fact. Let me just search for it. Okay, what is CMake variable for linking, or like for toggling shared libs, I guess? Build shared libs, yeah, there we go. So we could basically set that, and also how to override it in CMake. Force override it in CMake script. There you go, set. So I'm just gonna copy this guy. 10 watching now. Oh my god, that's great. Okay, so let's go here and let's add this. So set build shared libs. If you set it to on, then it would basically force all libraries. Watch him making big, yeah. Hello, Critique C. Welcome to the live stream. Build shared libs on or off. So by default, it's actually on, but we could turn it off and hopefully it would link all libraries statically. And let's see if that works. Build shared libs. On, off. Apparently it doesn't work on SDL, I think. But SDL, I believe, have its own thing for static linking. Let me see. SDL static linking. Okay, so there's SDL shared here. We could set it to off. So build or like SDL shared to off. And we should set SDL static to on. There we go. Because someone have actually asked me about this before in the comments. Build shared library off, build static library on. So now SDL would actually be forced to do it, which is great. Stable diffusion related. What do you mean? All right, let's try this now. Right now it's actually going to link it statically. There we go, perfect. So now if I actually took this application from here to here and then run it, there you go, perfect. Now let's just actually remove it right now. All right, let's actually make our first window already. Enough. Let's see. So main.cpp. Now here's the member function can be made static. No, thanks. Okay, let's see what we got here. So SDL window. Now here for SDL window, I'm gonna use std unique ptr to like deconstruct it automatically. Though I'm gonna do it like this. Null ptr, SDL destroy window. Okay, perfect. Now we do need to include memory header here. There we go. So basically unique PTR SDL window, and here we take the type of SDL destroy window, the type of the pointer function, right? So this is kind of, I'm not sure if I could show you how, but like basically here you need the type, and the type of this function is, it's kind of like its signature essentially. What is the signature type of this? Oops. What is, hold on. What is the signature type of this? Huh. No, tell me the function pointer. There you go. So this basically is equivalent to this, but it automatically does it for us here using the decal type. So that's basically it. Here null PTR, we initialize the unique pointer as null first, and here we basically initialize the deconstruction lambda or function with SDL destroy window function. So right now when this unique PTR goes out of scope, if it does have anything here, it would actually destroy it. So that's great. All right, next up, we're gonna need to actually say window.reset SDL create window. Let's actually remove this and let's say code.chaco. And here we need the width and the height. So the width, let's say 100, 600 for the height. And for the window flags, we're gonna go with SDL window Vulkan because we're gonna be using Vulkan. And SDL window resizable to make it resizable, and also SDL window hidden. Why hidden? Because I don't want to show the user a black window while we're still initializing Vulkan, because it takes quite a lot of time actually to initialize it. So they're just going to be seeing a black window in Windows. On Linux, actually they're just going to see trash on the screen. So why do that? Let's just hide it, and then when we actually run the application, we're gonna go ahead and say SDL show window after we're done the initialization basically. So window, but of course window here is actually a unique pointer, not really an SDL window, which this expects. So we need to actually unwrap it into its original type by using get. Otherwise you could also do it like this, I think. Cannot convert. Not sure why that doesn't work. Weird. But anyways, this works like this. Fine. And that's basically it. Now let's see if we got a window. And there you go. We actually got a window, but it just closes directly, really quick, because there's nothing like keeping it. We're just creating a window, and then we're initializing the app, which does nothing. Run, it shows the window, and then we quit the application immediately. Now what we need next is basically a loop to keep it going. So we're gonna need a bool running thing here. Game loop time. Oh yeah, exactly. So running, it's gonna be true by default, right? And basically what we're gonna do is while running, we're gonna loop through all the events in the queue that we have in this frame. We're gonna process them all, and then we're gonna get into rendering. So while running for SDL event SDL pull event. So this is basically equivalent. This may be a bit new for some older folks of C++. Like, it's basically like this. It's equivalent to this, while SDL pull event. So this one right here, using the for loop, I could actually basically declare the variable inside of here. Actually, this is not really a new feature. It's just that something not a lot of people know. But yeah. And then we say SDL pull event here. Anyways, so while running for SDL event, SDL pull event, and here I could actually handle that. So we're gonna say if event.type is equal to SDL event quit. Then we're gonna basically say running is equal to false. And when running equal to false, that means this while loop would go off. And so we're gonna go off this run function, and so we're gonna say exit success. Can I actually do exit success here? Yes, I can. Perfect. All right, let's try this now, I guess. Let's see. And there we go. Right now we have our beautiful window. Perfect. Okay, one other thing that is nice about my CMake setup here of actually building SDL yourself using CMake instead of actually getting a binary and stuff like that is debugging. You could actually see how SDL does its own thing. You could debug SDL itself or any other library in your project. Let me show you what I mean by that. So for example, if I go here and I put a breakpoint here and I run this. Okay, so notice the magic here. I could actually go inside of this, step into this, and then step again. And there we go. Right now I'm inside of SDL own source code. And I could actually see how SDL does the initialization and so on, which is insane. All right, so this is what SDL does under the hood. And you could basically go to line by line and see what SDL exactly does, and you could see all the variables that is going on, everything, pretty much. Wait, what? You didn't notice? It's because I'm building SDL from source code through CMake here. That's why. And in fact, I'm gonna build in everything from source code using CMake in this project, in this guide. Is that legal? Yes, it is. So that is amazing, actually. To be honest with you, just for the sake of completeness, I really wanted to avoid this, but I guess I'm just gonna handle the error checking anyways for the sake of teaching, I guess. So here's how I'm gonna handle this. Of course, there's a lot of ways to handle this, but I guess this is my way. I'm just gonna create an SDL exception class, public SDL runtime error, and then I'm gonna include, of course, std except for that, and basically inherits from runtime error because it is a runtime error. And then what we're gonna do, public, I think, right? Let's see what the AI would do here real quick. It didn't do shit. All right, there we go. Cool. But it didn't do that thing, interestingly. That's weird. All right, fine. Let's just say std string message. There we go. std runtime error message. So basically, I'm initializing the base class here, the runtime error, with our message here, and then okay, std runtime error message, and also I'm gonna include like SDL get error message, right? So the error message from SDL itself. But to get that, we need to include format here. And now I could actually use format. I could say std format SDL. How I'm gonna do this? Let's see what the. All right, cool. But no, that's not enough, really. I'm just gonna go with the message that we got from there, and then I don't know. Let's just do this and then do SDL get error. There we go. So basically, our own custom error message concatenated with SDL own error message. That's basically it. Did I miss anything? Let's see. We could make this class final. Fine, why not? And now what we could do is if so true on success. So if not SDL init, then we could throw SDL exception, failed to initialize SDL. Okay, cool. So this is our own custom message, and then it's going to be concatenated automatically by our own SDL exception to the custom error message from SDL itself. And here, same thing, I believe. So true on success, yeah. So if not SDL Vulkan Lloyd library, we're going to throw an SDL exception. Failed to load Vulkan library. Perfect. Now, of course, since we're throwing in exceptions, we want to actually handle them. So how are we going to do that? I'm going to say try here in the main function. And then, of course, catch. We could log an error using SDL log error. Why not? We could also make a message box. SDL shows simple message box error. This is basically for the error flag, like the error icon. Error, and then you give it the message, which is going to be one of our own messages here. But yeah, window null ptr. And yeah, that's basically it. And maybe even for the actual, can we throw it again? I think why I want to throw it again, so I can get like the breakpoint backtrace. But anyways, honestly, fine. Just leave it as it is right now. We're gonna return exit failure, fine. All right, so that's basically it for that part. How about SDL show window? True on success or false on failure? Honestly, for such functions, I'm not gonna handle the errors because it's insane. It's just gonna become spaghetti. But yeah. All right, so we're pretty much done. Well, almost done, I guess, with the SDL part. Now let's go straight into Vulkan. All right, Vulkan. Where to even start with that? We're trying to draw a triangle before dawn. I'm not gonna take the regular or classic tutorial path of going straight to a triangle and then risking everybody rage quitting. Directly, I'm gonna go like step by step. We're gonna start with clearing a window with a color. We're gonna have like a breathing red color, just like in the style of Vulkan. We're gonna be using memory transfer commands of the GPU to do that instead of graphics pipelines. Because, well, the graphics pipeline needs quite a lot of code before we could reach to a triangle. And then after clearing the window with a color, we're going to go straight into loading images using SDL image. And then we're going to blend it to the window. Again, only using GPU memory operations. So we could actually get used to how like you execute operations in the GPUs in Vulkan. And then we're going to look into how we can compile shaders at runtime using GLSL lang library. And of course, then we're going to get into the graphics parts. So instead of going straight into a crazy triangle, which you're not going to understand anything, I'm going to go like step by step, which is usually not done. I'm not sure why, but here we go. Hopefully that makes sense. Let me know if you guys have any questions or suggestions. My tutorials are very adaptable because, well, it's really not scriptable. You're seeing every error of mine and like you're seeing everything like in real time. So yeah. I did write this, by the way. Declaring the window would take like around 300 lines. So we got around 250 lines more to get like a window with a color on it. So yeah, using Vulkan, of course. So that's basically it. Okay, let's actually start right now with setting up Vulkan. So the first thing that we're gonna need is the Vulkan headers. Now, usually people here, what they do is they rely on the SDK to give them, oh boy, gonna be quite a long, yeah. So usually people rely on Vulkan headers from the SDK, but I'm not gonna do that because the people that's gonna like compile your projects and so on doesn't necessarily have the Vulkan SDK installed. The Vulkan SDK is basically just for the developer himself, right? So what we're gonna do, we're not gonna rely on that. We're gonna actually copy this guy right here. So let's go ahead and do this. So before SDL, let's actually say Vulkan headers and cpm add package Vulkan dash headers. You could either use the releases here by going to tags and then copying one of these releases, or you could again do the commit thing, right? In this case, I think it's fine to just go with the version, honestly. So we could just do this here, come here, and then do this. So here we're taking the latest version of the Vulkan SDK headers. Perfect. The next thing. Now, usually I would also need Vulkan right here to actually load the function pointers of Vulkan efficiently for maximum performance. But since we're going to be using the Vulkan HPP, we don't really need it, because Vulkan HPP does its own function loading itself, which is pretty good, all right? So we're not gonna need Vulk either. We're only gonna be needing the Vulkan headers. All right, so let's get straight into it. And of course, we're gonna be using Vulkan RAII, which is like, there's no tutorials about it pretty much. It's not used a lot. Most people only use the Vulkan C header, or at the very least, they only use the Vulkan HPP header without the RAII part, right? But yeah. Okay, so here, what we're gonna do, did it actually reload the CMake or not yet? Vulkan headers, oh yeah, I forgot. List append Vulkan dash headers, and now we should have access to it. There we go. And we're gonna go with Vulkan HPP. HPP, well, where is it? Huh? Oh yeah, Vulkan.hpp, my bad. There we go. Perfect. So the first part of this, can you just use the headers without having the SDK installed? Yeah, it is, because I'm actually like cloning the Vulkan headers themselves directly into my project. So you don't need the Vulkan SDK installed, but as I said before, you do need it because we're going to be relying on the Vulkan configurator and other tools in the SDK ourselves to debug this. But like anyone else, if they don't need those tools, they could just like generate the CMake and build the project directly without any problems. So yeah. All right, so the first part is the context. So VkRAII context, but what the heck is going on here? Hold on. Why this is not showing up? I guess let me first of all run this real quick. Okay. Now let's see what's going on here. Vk. Oh yeah, my bad. I need the RAII part. Okay, so RAII.hpp. Here we go. RAII context. There we go. So one thing about the context is that the thing is about Vulkan HPP is that they have their own Vulkan library loading tool, right? But we don't want that because we want only SDL to handle the loading part for us. for cross-platform stuff. So what we're gonna do, we're gonna make sure that's disabled. So I'm gonna copy this part right here, and I'm gonna do define this to 0. So it doesn't include that loader tool, that dynamic loader tool, because we don't need it. But then we're gonna have a little problem here, because with that variable n, you could actually create a context with no parameters, right? But since that's not possible anymore, there's only one constructor which takes a function of type vkGetInstanceProcAddr, right, or address, right there. So how we could fix this? Well, we could either use std optional and keep it on the stack, or use std unique ptr. Now, usually a lot of people I see really abuse smart pointers when it comes to C++. I'm not really sure why. In this case, I see it's perfectly fine to just use the stack with optional. And so it's going to be like initialized as null ptr, and then we can reset it. Just like here SDL window, although SDL window we do need it like the unique ptr there. But anyways. So now we're gonna say context dot in place. But before that, actually, we want to get the Vulkan function from the library here, from the DLL. So how are we gonna do this? Well, SDL Vulkan, hold on, vk get instance proc addr. There we go. SDL Vulkan get vk get instance proc addr. So this get the address of the vk get instance proc addr function. This should be called after either calling SDL Vulkan Lloyd library, creating SDL window with SDL window Vulkan flag. By the way, when you actually create a window using the SDL window flag, like Vulkan flag, it automatically loads the library if it's not. But it also means that like you can't really tell between the difference between the errors of the like Vulkan library not existing and the window itself erroring. But yeah, other than that, we should also make sure that the window is set up correctly. If not window, then we're gonna throw an SDL exception there. Auto vk get instance proc addr. Now this would gives us an SDL function pointer, which is just a void type, like it doesn't really have a meaningful type, because this could be any function. But what we're gonna do here, we're gonna actually reinterpret it to its own type here. So vk pfn, get instance proc addr, or can we just say pfn vk get instance proc addr? There we go. Perfect. But what the heck happened here? Hold on. Well, it's supposed to reinterpret this guy right here. There we go. If you want to know more about this loading stuff part, it's not really necessary. It's like something that you do just once and you forget about it, so you don't even need to understand this stuff. But if you really want to understand it, then I recommend Vulkan registry, hold on, loader guide. I think let me try to find it here. Yeah, the Vulkan loader here, and I think it's right here, docs. There we go. Okay, so I recommend these MDs right here. Like, I think this one, loader application interface. Yeah, this one, exactly. So I'm just gonna put it here on the chat, and you could read it out if you really want to know more about how this stuff works. But basically, just to put it simply, is that like, whenever you call a Vulkan function directly, what happens is that the driver, or like, should I say the loader, the Vulkan loader should like keep track of which driver you are trying to call basically, and then redirect you to that, which of course have a lot of overhead, like you're going through multiple function calls until you reach the driver. But when you actually load the function pointers directly into the driver, it's way faster, because like you're gonna skip all the steps and call directly into the driver. That's why we load the function pointers directly. Now in C, you would either do that yourself or use the Vulk library that I actually told you about earlier, this one right here. But in our case, since we're using Vulkan HPP, it also does it for us. And in fact, this context here, this is the part that is responsible for it. It actually goes ahead and it uses our function here that we gave it from the DLL that SDL loaded. Like it goes, hold on, let me show you. It goes ahead and it like, hold on, let me actually put a breakpoint here and show you exactly what's going on. Let me see. Come on. All right. Now I'm gonna step through this. Yeah. Oh, whoops, hold on, I missed it. Whoops. So I'm gonna get inside of this, and inside of that, I'm gonna get out of this, then get inside of this. Hopefully get, what the heck is going on here? Oh yeah, my bad. I actually haven't done it yet. Let me actually get into the context first. There we go. So context.inPlace. So I'm going to construct the context in place into this optional type right here. So context.inPlace. And I don't need all this crap really. I think just give it directly the vkGetInstance proc.ddr and this should work. This is kind of like saying vk RAII context vkGetInstance proc.ddr. It's just that since we have an optional, we're actually using inPlace function here to construct it in place. That's basically what's happening here. So yeah, pretty much. Now, in fact, we could maybe see here. Okay. Nah. Here's the deal. Honestly, what I'm gonna do instead, I'm gonna come here and check this out. So we have mDispatcher, context dispatcher. There we go. So this is the code right here. It's basically using that function that we give it to load vkCreateInstance function and vkEnumerate extension properties and these other functions. Why? These are like the global functions, the global Vulkan functions. But yeah, as I said, if you really want to know more details about this, I'm not gonna waste any more time about this stuff. You could read about this here. Anyway, so that was it for that. Right now, since we initialized the context, we could actually call our first Vulkan function finally, which is the enumerate version. So we can get the Vulkan version that we're using here. So how are we going to do that? Well, Vulkan version context enumerate. And since we're using RAI here, instead of like just saying vkget instance version and so on, it is actually a part of the context itself. It's an instance function, right? The other nice thing about RAI is that it gives you the ability to create multiple Vulkan devices easily, because both have, like, each device have their own dispatch tables already. So you don't need any kind of extra setup like in the C part. But yeah, anyways, right now the Vulkan version is just a UN32. Now we need to basically extract the major and etc etc. So like major version is, we basically use this vk version major macro, though this one is deprecated. I think maybe API version major. Yeah, there we go. And we just pass it that, and let's grab the minor. And now let's use std print line. This is the newest function, I think in C++ 23. Though to get that, instead of format, we're gonna go with print. And print already includes formats, so that's fine. So print line, Vulkan version, or just, you know, just say Vulkan, dude. And there we go. And to be honest, coming to think about it, we could just say this directly. And there you go. Come on. Alright, now let's actually run this and we should get the Vulkan version. And this should be our first call to Vulkan. There we go, Vulkan 1.4. Perfect, great. Now the next thing we're gonna need is to create a Vulkan instance. And a Vulkan instance is basically like our entry point. Like every application that wants to use Vulkan needs like a key into the API, and it's basically called the instance. And the instance, you basically declare your intent, because like Vulkan is very explicit. It wants you to declare everything you're gonna use beforehand, and this is the same thing when it comes to the Vulkan instance. Like you have to tell it which extensions you're gonna use, etc etc, and which features you're gonna use of the API by creating a Vulkan instance. But yeah, alright, so Windows set Vulkan version. Now I'm actually gonna do this right here in the init function right now. So we're gonna say VK RAII instance, but well, of course that's gonna go here. So std optional again, because we're gonna have the same problem there. So the same solution. So instance.inplace, and here we're gonna need the context and then the instance create info. Okay, so the context and the instance create info. All right, let's see. VK RAI, or actually just VK instance create info. And there's quite a bit of properties there, but I'm not gonna waste my time on those. I'm just gonna set the ones that are necessary for now. And one of them is the application info. And even the application info have quite a lot of properties here. So application info, as you can see, there's API version, application version, engine version, all this stuff, but they're all optional. But I do want to specify my application version, the API version that I'm going to use in this instance for my application. So in my case, it's going to be, I'm going to make actually a variable here, a const_xpr variable, basically a constant, Vulkan version. Emma have to go, get a snack, go to bed. It was nice catching you on stream for once, hopefully not the last. Thank you, Nacho, for coming to the stream. See you in the next one. Goodbye. Vulkan version, right? And here we're gonna say vkMake version. Well, actually, let's go with vkMake version, I think. Make API version, there we go. It's funny, I never in a million years would have expected for the only Vulkan SDL, C++ content nerdy shit ever I could find on YouTube, hosted by a guy from the same country as I. Yeah, there is quite a lot of surprises. Alright, so for the variant, you're going to go with 0. And the major, I'm gonna go with 1. Respect to you, restored my faith in this country. Thank you too. All right, 1 4,0. Okay. So I'm gonna be using 1 4, though you could also use 1 3 without any problem. If you want to use 1 2 or the other ones, then you may need some extra tweaks, but other than that, it should work as long as you fix the errors and so on and research yourself. But I don't really care that much about backwards compatibility, at least for now. Especially as a beginner, you shouldn't really care. As long as it works on your machine, it doesn't really freaking matter, you know? So that's all I'm gonna say. If you want to go into that rabbit hole, you're never gonna finish, because I've done it myself when I was a beginner. And in fact, I'm still a beginner to some degree, but well, we're learning. Anyways, so application version is equal to Vulkan version, and then we're gonna say instance create info dot version p application. There you go. Well, actually, for this one, I'm gonna use a function here. Set application info. Application info. Or honestly, it really doesn't matter, I think. Just set it directly, really. Yeah, fine. Just set it directly. Alright, so basically the instance, there's also some other stuff here. Instance create info dot. So there's flags, there's enabled extension count, the extensions that you want to enable for your API here. And enabled extension names, layer names. There's also layers. Now layers are interesting. Now usually most tutorials, what they do here, they would talk about something called validation layers, because without validation layers you wouldn't get any errors about if you're using the API wrong, right? But in our case, I'm not really gonna bother with enabling those layers, validation layers, oh my god, programmatically, right? I'm just gonna use the Vulkan configurator. As long as you have this open and you make sure to set this to any running Vulkan executable, and then you set this to validation here, you're gonna have them on automatically without having to. Now the nice thing about this is that you don't have to add extra code to enable them or disable them. And here you could actually easily enable and disable. Well, hold on, this one you could easily enable and disable. If you want to disable, you just set to no Vulkan executable. Now, why they're not like why you have to enable them? Because they're actually like you get a performance hit for the validation layers, because the validation layers basically, instead of calling into the driver directly, you go through the validation layers here, you call into them, and those validation layers call into the driver for you. But before they do that, they actually analyze your arguments that you're passing to the driver and stuff like that, and they would basically give you warnings or errors or whatever if you're misusing the API. So that's their job. But of course, because of that, they have some overhead, so your application would be slower while they're active. Basically, that's all you need to know. So I guess that's all for the layers. For the extensions though, now the thing is about Vulkan is that it doesn't assume anything about how you're gonna use it. It doesn't really assume anything. So like you could use Vulkan for headless, like basically without any window, without any display system. But in our case, we are going to use a display system. We're going to use a window, right? We want to render to a window. So we need some extension called a surface extension. You could read more about this extension if you really want to. You could just search up the vk surface, or like surface extension Vulkan registry. Could just search about this and read about this like extension right here. You could find all sorts of stuff here. And then here a description. Extension is an instance extension. It introduces vkSurface objects which abstract native platform surface or window objects for use with Vulkan. It also provides a way to determine whether a Q family in a physical device supports presenting to a particular surface. A physical device is basically any device that is running Vulkan. It's usually a GPU, but it could also be a CPU if it supports Vulkan. Like there is, for example, a driver called Lava Pipe on Linux, and maybe you could also use it in Windows, I'm not sure. But basically that driver emulates or like implements actual Vulkan API for the CPU. Of course, it's not going to be as fast as a GPU, but well, it's going to work, I guess. So yeah, separate extensions for each platform provide the mechanisms for creating vkSurface. Now the problem is you don't need only this extension to make it work with Windows. You also need a platform-specific extension. In our case for Windows, it's going to be vkWin32. Win32, well, Win32, yeah. So like vkWin32 surface extension registry. In Windows, you're going to need this extension too, along that extension. There we go. Is an instance extension, provides a mechanism to create a vkSurface object defined by the vkChr surface extension. So it basically includes HWND as well as query to determine support for rendering to the Windows desktop. All right, but we don't really need to mess with this stuff. Like this stuff would be handled by SDL for us. So don't worry. We're not gonna teach you Win32 here because that's another rabbit hole. All right, so where is it? Let's see. So we're gonna set the extensions. So enabled extension count is equal to, well, we're gonna first of all make a UN32T extension count here, right? And we're gonna use SDL Vulkan get instance extensions, and basically we're just gonna give it the count here. So extension count. So here we're giving an address to a variable, to a UN32, and it's gonna basically put the extension count that we're gonna need for the Windows to work here. It's usually gonna be 2 in this case. It's gonna be the vkSurface extension and also the vkSurface Win32 extension. So it's usually gonna be 2, but we don't bother with that. Other than that, this would also return for us the actual pointer to an array. So this would be the actual extensions, but honestly I'm gonna set it directly here. So instance create info dot extensions pp enabled extension names is equal to this, right? And after that I'm actually gonna set the enabled extension count to the extension count I got from the function here, and there we go. Just to show you even more, to show you what's going on here exactly, because I'm aware this could be a bit hard to grasp. All right, what's going on here? First of all, we have some problem apparently for whichever reason. Oh yeah, so this is actually expecting the instance here. To create an instance, the constructor is expecting a VkRAI context, but it's getting an optional VkRAI context. So we have to dereference that to get the original value. And I'm just going to dereference it like this. Otherwise, you could also say .value. Now, of course, this could segfault or whatever if the value isn't there. But here we already know that's like not possible in this case probably, so we're just gonna go with this, right? So yeah, all right, let's go ahead and run this. And there you go. So as you can see, extension count right now is just have some garbage value here because it's not initialized yet.
But after I'm gonna run this here, and also notice the instance create info here contains the extension names pointer here is null. But after this function call, as you can see right now, it actually contains something. And in fact, I could probably set how much. And also the extension count here is equal to 2. So I could actually debug this here. I could, since this is a pointer, the debugger doesn't really know how much elements is here. So I have to actually tell it. So how I'm going to do that, view as array, and I'm going to give it the size of 2. And there you go. As you can see, there's vkChr surface and vkChr Win32 surface. And of course, I'm going to set the instance create info. I'm going to give it the count 2. And there we go. Perfect. So now we have those two informations in place. And then we're going to construct the instance. And since there was no exception, it means that we have successfully created our Vulkan instance, which is great. Now, another way to verify this, which I think is very useful for a beginner, is to switch to the API dump layer here, because there's quite a lot of layers here for different things. The validation layers, as I said, is for like it basically tells you if you're using the API right. The API dump, on the other hand, it basically just logs all the function calls that you're emitting into the API. So in my case, as you can see, I have only one function call into Vulkan so far, which is vkCreateInstance. I'm giving it these arguments and the frame 0. Well, we have no frames yet in the thread 0, and it's returning vkSuccess, which means it's successful, right? So vkSuccess is basically 0. Anything below 0, anything negative is an error code. Anything positive is a warning. And yeah, that's basically it. And notice the other properties that we haven't set is either null or 0, which is great. And here our extension count is 2, and our extension names is correct. Perfect. So there we go. Alright, so what we're gonna need next? We're gonna need to create the surface. So for the surface is also the way to create it is cross-platform dependent. So again, we're gonna make use of SDL help here. So SDL create, or like SDL Vulkan, I think. Vulkan creates surface. There we go. So here it needs the window. But of course it doesn't want the unique PTR, it wants the actual raw window, so I'm gonna like dereference that there. And for the instance, same thing, though for the instance here it's quite interesting. Now here what I have is an optional VkRAII instance, but Vulkan create surface is a C API, right, of Vulkan. It expects a raw handle without any fluffs, right? Any RAI fluff, right? So I'm gonna like dereference it once to remove the optional, and then dereference it twice to remove the RAI, so I can get the raw handle. And to do that, I'm basically gonna do this. So basically dereferencing twice. Once to remove the optional, and the second time to remove the RAI wrapper, right? So I'm gonna just get the handle, the raw handle, raw C handle. The next thing is the allocation callbacks. We're just gonna set as null PTR. You don't have to worry about that one. Apparently we have 4 parameters. Yeah. So here you actually have an out parameter of surface. Actually all C Vulkan APIs use out parameters to give you the instance, and like the return to give you the actual errors or success codes or whichever. So here I'm gonna say surface, so vk, and here I need a raw surface type, so vk surface khr. There we go. Can I actually do this? I'm not entirely sure. No, I don't think so. Probably not. Yep. Nope. Alright, so what's up here? Actually, no, I can't do this. Probably I want to do this instead. I guess. Not value.get, sorry. .get, yeah. Alright, so this of course could fail. So what we're gonna again do if not, then we're gonna throw an error here. Throw SDL exception, failed to create Vulkan surface. And after that, we actually want to make this into an RAII version. So how are we gonna do that? Let's see, cd optional vkRAI surface khr surface. Now we need to understand how we could actually take a raw surface handle and convert it into an RAI version. Well, these RAI version actually have a constructor for that. So surface.inPlace. Oh yeah, I see what's going on here. So this is the raw surface, right? The raw surface handle. And now it's actually in place. So as you can see, this is the constructors that we have available. So it needs, first of all, the instance RAI. So, and to get that, we're just going to dereference once to remove the optional. And then finally, we're going to give it the raw handle, the raw C handle, like that. And there we go. Perfect. Lovely. Is there anything we could actually get out of this? Let's see. Oops. We could actually do this. Nothing very interesting there. But anyways. But the one interesting thing about this is that once the application get destroyed, the surface would also get destroyed and would automatically destroy the surface handle, like the of Vulkan, right? It would automatically call vk destroy surface for us instead of us having to do that. So now if I actually make sure that we are on the API dump, you can notice that we're going to be calling much more API calls now. I'm going very slowly right now because this is the start, but hopefully I'm going to speed up my pace very soon. So create instance, and here we go. Create Win32 surface. This is what SDL is calling behind the scenes, and it's returning vk success, which is perfection. So it's giving us it's giving it the H instance of our application, the HWND. Let me know, by the way, if you want me to make a tutorial about Win32 to actually understand what this crap means. But anyways, and yeah, that's basically it. Now, if we actually exit the application, you're gonna notice other function calls right now, which is vk destroy surface khr. So this is part of the deconstructor of the RAI. So once it's deconstructed, it actually called this automatically for us. And again, it called destroy instance too. And there we go. Perfect. Alrighty, so that's basically it. Let's make sure we have no validation errors. I don't think we should, but just making sure. There's also some other options here when it comes to the layers. As you can see, there's no errors. But there's also other options here. If you go down, you could find that you have info, warning, message severity, performance, and error. Like you could, for example, take all of this on, and you're gonna have all sorts of messages, not just errors. And as you can see, oh, what the heck is going on here? Oh, we have some problem or what? Hold on. Oh, never mind, because it's basically just breaking there, although it's an info message. I'm just gonna disable it. It should be disabled by default for you. It's just that I was using this. I'm gonna get into this in a second. But let me just do this now, and there you go, no problem. Alright, so we have only one message, which is of type info, and this is just some weird stuff. I don't even know what it is, but nothing crazy going on. No warnings, no nothing. Okay, cool. The other thing is, let me just remove the info. Keep warning, maybe. Performance not needed for now. And there's also this best practices if you want that too. Like we could actually try that. Hold on. If I do this, let me see if there's any messages so far. Not really, but we could show that later on. But for now, let's just disable it. And there's also this break right here. If you actually turn it on, and if an error actually happens, it would automatically break there into the function call. As you can see here, it did it here with the info message. But yeah, so that's basically it. All right, let's get to the next thing right now. So we got our surface and we got our instance. Next is we need to pick the GPU that we want to use, or shall I say the physical device that we want to use with Vulkan. So I'm not like usually tutorials would go ahead and do all sorts of things to pick a physical device, but I'm not going to waste time on that for now. I'm just going to pick the first physical device, and I really recommend you do that as long as it works on your machine, so you don't waste time pretty much. I'm trying to only explain to you the things that other people wouldn't. So the other thing is you could just look it up yourself, or I'm going to explain it later if we need it in the future, basically. But other than that, let's see what we need. So, by the way, one little thing before we go forward with this is that we could actually use functions to make this way more organized, more readable. So for the instance part here, we could just call this init instance. Right, and so we could have a private section here, and we're gonna have void init instance here, and we're gonna paste that stuff there. Okay, the same thing with the surface here. So right now, if you notice, this would really be way clearer for you guys to see what steps we have done so far, and also for me as the teacher. But yeah, init instance and init surface. All right, so that's basically it. Just for organizational purpose. Next up, we need to pick a physical device. Perfect. Let's actually pick a physical device now. So pick physical device. And later on, in fact, if we really want to, we could actually change the code here to be more sophisticated later on. Or, hold on, let me see what's up. Not really. A big physical device. So we're gonna get all the physical devices from the instance. So we're gonna enumerate all of them here. I only have one physical device, so it's gonna be only one element. If it's empty, then well, there's no Vulkan devices found. So we're gonna throw an SCD runtime error. And well, what the heck is going on here? All right, never mind. Let's see what the AI would actually do here real quick. Let me see if it's gonna do anything interesting. Not really. It's kind of trying to go through all the physical devices. In my case, I'm not really gonna do that. I'm just gonna have like, is there a VK RAII physical device? Yes, there is. Okay, perfect. So what I'm gonna do is physical device in place, and it basically gonna need, I think, the instance. Yeah, there we go. Cool. It's gonna need the instance and the physical device here. This is front to just get the first element in the vector, basically. And that's essentially it. So now we should have our physical device. One thing we could do is like we could, for example, I mean, in fact, there's a lot of properties that you could programmatically get through Vulkan. In fact, anything here, right here, you could actually get programmatically here and basically pick a physical device depending on that, right? All sorts of things like the supported extensions, the features, the properties, the key families, etc. In our case, I'm just gonna go and print the device name that we picked here. So physical device dot name. Well, I'm gonna use this. What the heck? I think I need to get get properties dot name, device name. Now this is an array wrapper 1D, so it's a character array, not really a string. If you actually try to print this directly, it would just be a list of numbers, right? Which is not exactly what we want. But let's store it first. So raw device name. This is the raw device name in a fixed array. And to actually get a string out of that, we could say .data. This actually wouldn't work as expected, but let's just go with it to show you the problem here. And yeah. And then we're gonna print it, basically. Yeah. So let's see what's gonna happen here. And there you go. We actually did get the name, but we also got these invalid characters. These are basically null characters. So what we actually need to do here instead, because this is like basically a fixed array of 256 characters per the API. But what we really want is to use std sterling to get like the number of characters before the first null character, essentially. So yeah, is there no strnlen? No. Okay, never mind. Let's just go directly and say raw device name. There we go. And that's basically it, I think. In fact, we don't even need string here because like the name is already owned, but yeah, whatever, it doesn't matter really. Never mind. Let's just go with this. So this should work now. And there you go. So now we're picking a physical device. Perfect. Next up is we should also pick a key family. Now honestly, I'm gonna pick a key family here too. But for now, we're just gonna pick a 0 for the graphics key family. So what we're gonna do here is uint32t graphics key family index and present key family index. So these two for now, I'm just gonna hard code them. And maybe let's even say a transfer key family index for later. We could also have a compute. Honestly, let's not overcomplicate things already. Let's just keep graphics and present only. For now, what I'm gonna do, pick physical device, and here I'm gonna actually do that stuff. So like graphics key family, I'm just gonna hard code it to 0. Like most devices, in fact all all devices would have the first key family, which is index 0, would support compute. Not compute, graphics. How you could actually verify that, if you go to your VulkanCapsViewer that comes with the SDK, and you check out this key family part, you're gonna see, so in my case I have 6 key families, right? And here's the first key family, which usually supports most operations. Graphics, in my case it's graphics, compute, transfer, and sparse binding. And there is 16 queues there. And this is some granularity stuff, doesn't matter for now. And if it supports presentation or not to the screen. How can you think about these key families is like teams or groups. Like let's say you have a company, right? And you have teams, you have designers, you have programmers, and you have all sorts of teams. Like every team have their own capabilities, what they're capable of. For example, this team is capable of graphics. They're capable of drawing stuff, right? This other team is only capable of transfer operations. Though, by the way, all the key families are capable of transfer, but since this one is only capable of transfer only, and there's only 2 queues here, this is probably a dedicated DMA transfer queue, which is basically means a fancy way to say that it's very fast to transfer stuff with it. So you probably want to use this queue in this case for transferring, let's say, big textures and other game assets to the VRAM, because, well, you have 2 sorts of memory. In fact, it's more complicated than that, but like the huge ones is that you have your RAM. In my case, it's 16 gig. So this is the system memory. And then you have your VRAM, which is the actual RAM inside of the GPU. So in my case, it's actually 6 gigabyte of VRAM. So basically when you load a game, the first thing that happens is that the game goes ahead and loads the textures. First of all, what happens is that the CPU goes ahead and load the texture, or should I say the image, into the memory, into the system memory. And then you use Vulkan to take that image from the system memory and transfer it into the GPU. Into the GPU VRAM. So you could use it from the GPU for graphics operations or whatever you want to do with it, basically. But yeah, it actually, for example, the VRAM actually is more complicated than that. Even the VRAM itself have multiple memory types, but we're not going to go through that for now. It's much more complicated anyways. But yeah. But yeah, that's basically it for that part. And for the present key family index, I think for now I'm just going to hard code it to 0. Later on, we may want to replace these with programmatically looking for the best key families, right? Though you got to be careful, just make sure, because this one is not guaranteed. You could actually not have the first key family not support presentation. So for example, this one supports compute and supports presentation. We could also use the key family 2 here, because we could do post-processing using compute here and then do presentation. Though if you use different key families, then you have to do more stuff on the synchronization part, which I haven't even explained. That's yet another suffering. But anyways, for now, I'm just gonna keep it very simple. 0, 0. And that's basically it for that part. Next is the logical device. So we picked the physical device. Now we have to request access to it by declaring the extensions and features we want to use on that device. So we can finally actually, tell the GPU to do stuff, basically. So pick physical device, and now we're gonna init the device. So here void, let's just do it here, I guess. void init device. By the way, is the stream fine? Yeah, seems good. Alrighty, so what we're gonna do here? VK device key create info, perfect. We're gonna set the key family index that we're gonna use. So basically here we're declaring the key family indices we're gonna use. For now, we're just gonna only use the graphics. Honestly, I'm just gonna remove this present so we don't get misleaded. Maybe I'm gonna put it back later on, but for now, let's remove it just to keep things very simple. Q count is equal to 1, no. So Q create info dot set Q priorities. Now this have an array proxy, no temporaries. This is basically you could pass it an array, a vector, or span, or whatever. Whatever kind of array like type, right? So what we could do here is you could say std array well float comma 1 queue priorities 1f, and then we could basically pass in the queue priorities here, and there we go. Though this seems to be not needed since it's just going to infer it for us, which is nice. And that's basically it, I think, for that one. Next is the device create info itself. So basically every queue family that you want to use, you're gonna fill out one struct of this type. And next up is this guy right here. So device create info. Here. We're gonna need to declare the extensions we want to use, which gonna like include the swap chain so we can render to the window. And what else? And of course we're gonna need to also include the the queue infos that we want to use. So let me actually say std array vk device queue create info, and apparently just inferred it for me here too. So I'm just gonna set the queue create infos to that queue create infos. And what's next? Device. Also, let's include the extensions now. Exactly. And here I'm gonna say device create info dot set extensions, enabled extensions, p enabled extension names. And actually I'm gonna copy this type hopefully, but yeah, just to match it. Very pedantic. But yeah, perfectionist. And I'm just gonna pass it there. We could honestly just call this enabled extensions, really. It's very clear that it's device extensions from the context here. But yeah, that's basically it. vkChr swapchain, this is the only extension for now for the device, and yeah, that's basically it, really. And finally, we could actually create it. So device dot in place, right? So here we need the physical device. So of course we're gonna dereference it, and then the device create info, and there we go. Perfect. And that's basically it to create a device. And finally, you're done with the context creation. This is, well, actually you're not even done. There's still way more, but this is, I guess, a big part of it. But yeah, oh boy. Oh boy, oh boy. Let me make sure there's no validation errors anymore. not anymore, but like there's no errors yet. Yeah, there's no errors. Perfect. Let me show you the actual API dump here real quick. And there you go. Vk create device, Vk success. Perfect. So let's actually grab the queues that we have declared to use. So vk RAII queue, graphics queue, but of course this should be a CD optional first. Okay. And then in the device, after we create it, we could just get it. So like graphics queue dot in place, and here we need the actual device, and we need the queue family index and the queue index, because you could actually request multiple queues from the same queue family, so you have to tell it which queue you're talking about, the index of that queue and that queue family index. In our case, we only request in one queue because we have one queue priority here. You could check out more information about queue priorities in the spec. I'm not going to go into it because it doesn't really matter in this case, since we only have one queue anyways, so the priority doesn't really matter. Okay, and that's basically it. Alright, next up, there's quite multiple ROIDs. We could go straight into the swap chain, or we could go to the command pool and the command buffer. I think I'm going to go straight to the command pool and the command buffer and leave the swap chain until the end. Let's go ahead and actually do that. SCD optional, vk command pool, and oh boy, command pool. There we go. Well, what the heck. SCD optional command buffer. Alrighty. So the command pool and the command buffer. And then we're also gonna need, I think, a fence, right? A fence. Yeah, exactly. RAI fence. I'm gonna explain this in a second, but hold on. Command pool, command buffer, and a fence. I think that's pretty much it. Is there anything else? Semaphore is not yet. And yeah. So let's actually create this stuff. So init device. After initializing the device in the queues, we're gonna go to initializing the command pool, and then we're gonna initialize the command buffer, or not really initialize, we're gonna allocate the command buffer from the command pool, or using the command pool. There we go. So yeah, let's do this. So void init command pool. So let's see if the AI could do this quickly. Command pool create info. Perfect. So we set the key family index that this command pool would operate on. Like, so basically every command pool should only be used in one thread, essentially. And you need to have, like, every queue family should have its own command pool, basically. But yeah, here we're gonna set reset command buffer, huh? Yeah, so we could like individually reset command buffers. But do we really need that? We could just like, yeah, we actually do need it. Yeah, we don't need it right now, but we're gonna need it soon enough when we're gonna have multiple command buffers. But without it, we basically have to reset the whole command pool. So let me actually explain this. So a command pool is kind of like a regular memory allocator. It's just like it manages the allocation of command buffers. Or command buffers are like to-do lists that we submit to the GPU to execute, right? Or like, yeah. So in OpenGL, for example, like let's say the APIs are actually chefs, right? Let's say OpenGL is a chef in a restaurant, right? So if OpenGL was a chef, you would actually give it orders one by one. So like whenever you have a new order, you actually tell it directly at that point what's the order you want, and then the chef should adapt directly to it, which as you can see is not very optimized way of doing it. The chef would go crazy for sure. And he wouldn't do his best job, like, and he would be very distracted because every time you have a little new order, you're gonna come, like the waiter would come and tell him exactly that order, and then come again and again and again, every time distract him and ruin all his plans and ruin his day. That's OpenGL as a chef, right? But like on the other hand, if we have Vulkan as a chef, Vulkan is quite, you know, I guess professional. He doesn't really accept that. He doesn't accept that childish behavior. He wants you, like, if you want to give him orders, you need to give it, like, you need to, first of all, type all your orders that you need to get executed into one to-do list, which is in this case a command buffer. And then you can submit that command buffer or that to-do list to the chef at once. And then the chef would see how he can execute that command buffer or that to-do list in an optimized manner without any distractions whatsoever. So yeah, that's basically what a command buffer is. It's really that simple, pretty much. All right, so command pool in place. None of the overloads except 2 arguments, apparently. Okay, let me see what's going on here. So, command pool. Did I miss the type or something? Yeah, I did, apparently. My bad. Alright. So that's why. So we give it a device and then the command pool create info, and there we go. That's how you initialize the command pool. Next, we need to allocate a command buffer from here. So primary. There's primary and secondary command buffers, but this doesn't really matter. Since it's 0, I could just omit it. It's by default a primary command buffer. Other than that, you have a command pool, a command buffer count 1. Now here what you got in place. You got device and command buffer and command pool. I see. So let's actually allocate this guy. I guess you have to maybe, hold on, let me see how to actually do this. Command pool dot, or actually do this, and no, we can't apparently. So how about this? Allocate command, there we go, allocate command buffers. And so this takes a command buffer allocate info, and then it gives you a vector of VkRAII command buffers. Okay, perfect. So command, sorry, allocate info. What is it called here? Just call it allocate info, really. Why bother? There we go. And of course this gives us a vector of command buffers. But in our case, for now at least, we only have one command buffer. Though we're gonna need multiple command buffers later. You know what, let's just keep it simple anyways. Fine. So command buffer dot in place, or I could just say equal, I guess. Can we actually use in place like this? And of course, let's just take the first command buffer. And we probably gonna need a device here, maybe. No. Weird. So hold on a second. So this is the command buffers. This is the command buffers. Let's see where are the constructors here. So the first thing first is the device, which we can give it like this. Next thing next is the command buffer, and then the command pool apparently. Cannot convert L value. And there we go. Perfect. Add const. And that's basically it, I think. Let me make sure there's no validation problems so far. And we should be good with that part. We also need to initialize the fence, yeah. Oh. Invalid vk command buffer. Weird. To be honest with you, let's not overcomplicate shit here. Let's just say cd vector, really. I'm gonna need multiple command buffers later anyways. So yeah, and we're gonna call this command buffers instead. In here, allocate command buffers, and so finally here, failed to allocate. Not really. So we're just gonna say command buffers is equal to this. And yeah, that's basically it. Right, the other thing is the fence here. So the fence is part of a class of objects called sync objects. Basically, they're used for synchronization. So init sync objects, void init sync objects. There you go. And here, so now let's actually create that info object. Fence create info. It needs to be signaled at first, and we're gonna know why later on. But for now, that's the flag that we're gonna put in, and finally fence in place. We're gonna create some other sync objects later on, but for now, for starter, we're only gonna need a fence. And that's basically it for the fence. Let's see now what's going on here. And my compilation time is a bit slow because I'm using software for the stream, like the CPU for the stream. Yeah, anyways. So now we have no validation errors, which is cool. Now last thing to finish up the initialization part, which is to actually initialize a swap chain. And swap chain basically holds multiple images, off-screen images, that gets rendered into the screen one after the other, right? So if you're coming from OpenGL, it's going to be like GL swap buffers, right? When you do this GL swap buffers, then like if it's double buffering, then what it does, it actually takes one image from the swap chain and presents it into the screen or into the window, right? While the other you render into it. The other one that is not on the screen you render into it. But yeah, anyways, let's go straight into it. Void init. Oh, actually, instead of init swap chain, I'm gonna call this recreate swap chain. Because this would actually can be called twice, or like not twice, but multiple times, in fact, to recreate the swap. Because we do need to recreate the swap chain if we have like, if the window gets resized, basically. So, and that comes to here too. But yeah, anyways, let's just say void recreate swap chain. Let's see what the AI would do, and we're gonna come from there. We're gonna need first of all the surface properties, basically. So vk surface properties, right? Sorry, surface capabilities. KHR. So as you can see, physical device gets surface capabilities. So every physical device have different surface capabilities, basically. And of course, every surface too. And finally, we're gonna take the swap chain extent. In fact, we're gonna store that one too. So here we're gonna have std optional. Oh no, what the heck? Swap chain, dude. And we're gonna have the swap chain images too. For the swap chain image views, we don't need that, at least for now. We're not gonna be rendering to it using graphics operation just yet, so we don't need those now. Other than that, we also need to keep track of vk extent 2D of the swap chain extent, basically. And so yeah, where's that thing? There we go. Okay, cool. So swap chain extent, no, what the heck? Swap chain extent is equal to surface capabilities current extent. That's basically the size of the swap chain in pixels. And finally, I'm gonna go with the swap chain create info. There's also another thing that we're gonna need for the swap chain is the format. So vk format, well, vk format probably this is what we really want here. Same thing maybe here. I'm not entirely sure. We're gonna see swap chain image format, and yeah, for the swap chain image format, for now I'm just gonna hard code it. Later on, we could basically do the exact same thing and look through the available surface formats here. If you go to surface here, there's some formats that are available, as you can see. For now, I'm just going to hard code it as BGRA8 sRGB, which I think is available on all platforms, I believe, but yeah. Though, honestly, there is some platforms probably that doesn't support sRGB, but if not, you could go with UNOR. But anyways, for now, I'm just going to go with sRGB. So vk format what is it called again? BH. Oops. BHGHRH sRGB BGR. Actually, probably we also want A8, right? Or no? Yeah, I could have easily missed that and got an error, but yeah. Other than that, I think we're good here. So after that, we're gonna create the swapchain create info. So the surface, of course, the minimum image count. We're gonna add a +1 here. You don't need to worry that much about that one. The swapchain image format, image color space, we could just hard code that. The image extent, image array layers. 1, this is used for stereoscopic rendering, like for example, let's say VR, where you have like two screens, kind of like one for one eye and the second for the other eye. You could have multiple array layers, like you could have multiple images in the same swap chain and render them using the same pipeline, just or like the same shader, just in different layer. But anyways, that's just a little something. Yeah. Exclusive identity, opaque, so true. Yeah. All right, let's see what we got here. This exclusive thing, this is basically if you're gonna be sharing multiple queue families, but we're not going to be doing that for now, and this is 0, so it can be omitted. It's by default exclusive. Same thing with this one, I guess. No, in fact, for the pre-transform, I think we could just set it to the surface capabilities can't transform. No, I think so. And here opaque, isn't this default? No, it's not, so we need it. Here FIFO is actually like guaranteed to exist, but the best, if it's supported, is mailbox, but you have to make sure you have that. We should have done that programmatically, of course, but for now I'm trying to cut off on the code. But in my case, I do have mailbox supported, so I'm good. I'm gonna explain more later maybe about the present modes and stuff, but for now this should be fine. Clipped equal to true. You shouldn't really worry about the other properties for now. I may revisit this and explain more about it, but yeah. Though you gotta be careful, I think, with Wayland, I think, on terms of image extent and stuff. But it should be fine for now, I guess. Maybe. Anyways. So create swap chain, clipped. And now the next thing is I'm gonna check if we already have a swap chain created. So to make sure to see if like this is this the first time that we create a swap chain, or this is like just another time, or we're just recreating it basically. How we're gonna do that basically is by if swap chain, because it's actually already optional, so we could just say has value. So if it does has value, then we could say swap chain create info dot old swap chain is equal to swap chain. Pretty much. Other than that, we should be fine. Alright, so next is swap chain in place device, swap chain create info, perfect. Swap chain images, get swap chain images, KHR. No, I think you probably just say swap chain get images. There we go. Perfect. Okay, so get images actually gives us back vkImage. And honestly, that's right. We don't want to own these images anyway, the swap chain images. So we shouldn't use the RAI types anyway. These images that we're going to get from the swap chain in this case are not created by us. You know, we're just supposed to borrow them, not really own them, which means we're not responsible of destroying them. And that's why we shouldn't use the RAI version anyways. So yeah. Get images, and what's next? I think that's pretty much it, right? Yeah, I think so. And if everything goes well, we should have a swap chain ready, and we should be done with the context creation stuff. And we should be able to start actually implementing the frame logic, the actual code that runs every single frame. And as you can see, there's no validation errors. Check the API dump. As you can see, yeah, there you go, vk success, which is perfect. Alrighty, cool. I guess now let's go straight to the frame logic, where the actual magic happens. This is just the initialization part where we're just preparing stuff up. And by the way, before I forget, let's actually handle the swap chain recreation real quick. So when the window gets resized, where's the... yeah, where's that thing? Hold on. Is this a game engine? Pineapple, welcome to the live stream. It is part of making a game engine, so we're just making a render. I mean, it could be a game engine, but yeah, part of a game engine to be exact, I guess. Renderer. Using Vulkan Graphics API, which is a low-level graphics API, a modern one, pretty much. And it's very high performance, though quite complex to use, or at least quite verbose. But yeah. Other than that, yeah, okay, so where's the event type stuff? Alright, so here we're basically having the handling of the events happening here. Actually, I'm gonna make this into its own function just for organization. So void handle events. There we go. Now instead of an if here, just checking the SDL event quit, we're gonna actually match on the event type. Sorry, not match, switch. Event dot type. It's match on other languages like Rust, but yeah. Generate a missing default case, break. Other than that, we're gonna need SDL event quit. So if it's an SDL event quit, then we're gonna set running to false and break. And if it's SDL window event resize, but like, how do you actually get that? There you go. Though I think pixel resized, I think, yeah, pixel size changed. Then recreate swap chain. So when the window size gets changed, we're just gonna recreate the swap chain, and there we go, pretty much. Right? Well, of course, let's not forget the case here. Case. And yeah, that's basically it. The pixel size, the window has changed to data 2. Yeah. Alright, so that's basically it for recreating the swap chain too. Let's make sure there's no problems here so far. And we should be able to actually start the frame logic right now. Logic that happens every frame. Oops, there is a problem. There's some validation errors. Hold on, let me see. Invalid vkCmdClearColorImage swap chain KHR object. If all swap chain must be valid. So apparently we're actually giving it a invalid swap chain for whatever reason there. in the old swapchain part. If swapchain has value, swapchain create info, the old swapchain is equal to swapchain. Let me see what's going on here. That should work. I don't. At first it should be, so has LU. Can I actually see what's happening here? Hold on. Let me just put a breakpoint there and see what's going on. So this, and where's our swap chain? There we go. Well, what the heck is this? There we go. Has value is equal to false. So it should work just fine. And then we place the swap chain with a new value, and now has value is equal to true. And we set the swap chain images. What? Something strange going on here. What is the error? It's just a validation error, really. Validation error, old swap chain parameter. Invalid vk swap chain khr object for whichever reason. If it's not vk null handle, then it must be a valid vk swap chain khr. So somehow, even though the swap chain have a value, it's invalid here. That's very strange. Let me check the API calls. Walaikum assalam Abdurrahman, welcome to the live stream. Is not available, possibly due to compiler optimization. Okay, let's see what's going on here. So for whatever reason, I got actually user mode data execution prevention violation. What the heck? Hold on, do I have that up and running? Okay. Okay. Actually, vk destroy swapchain khr. Yeah, it's probably dangling somehow. Something wrong in my logic here. Da, 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 da. Can we just ignore the old swap chain stuff for now and just create a new fresh swap chain every time? Should probably be fine for now until I figure out the problem of camera. Okay, let me see if there's any errors anymore. Yeah, so right now it's perfect. It's probably better if this works for performance reasons, but for now I'm just gonna keep it commented out until I figure out why it's to do. Alright, so other than that, we're good to go. Now we could actually work on the frame logic directly. Are you able to draw a triangle as is? Not yet. My first goal right now is not graphics operation, it's just clearing the window for now. So we go step by step instead of going straight into a triangle, which I think is more complex. But after that, that would be the goal, yeah. So alright, let's go straight into rendering. So after handling the events, we're gonna render. By the way, one interesting fact that you may want to know is the order of these functions. So handle events and render. So you could actually handle the events that render, or render then handle the events. Handling the events then rendering is better in terms of latency. It's lower latency because the new frames that you're rendering depends on the events that you had, the fresh events that you had. Otherwise, rendering then handle events is more into performance, but larger latency, more latency, or input latency basically. But yeah, let's not go into more detail into that, just food of thought, I guess. Alright, so void render. Now the first thing first is we need to reset the fences. So how are we gonna do that? Device. Reset fences. It actually needs a vector of fences apparently. And I mean, later on we're gonna have a vector of fences anyways, honestly. So let's just convert it already to a vector. Fences. So device, reset fences, fences. And for the creation part, init sync objects. Here we're gonna have fences. Well, let's see what's gonna do here actually. No, what the heck? Just say fences dot in place back. Device fence create info, and that's basically it. Okay. Cool. Now, cannot convert to parameter type vkFence. Oh, apparently it can't accept VkRAI fence, huh? Oh, that's strange. But honestly, it doesn't really matter, does it? Yeah, it really doesn't matter. You know what? Fine. Parameter type. Apply. There we go. Can be made constant. Okay, so we're basically getting the first and only fence for now, and basically wrapping it into a vk fence because it's a vk RAII fence. And then of course we're gonna actually wait for fences. There we go. Well, in fact, let me just store a reference to the fence really. So vk fence, or should I say, yeah, that should be fine, I guess. Oh yeah, there we go. And now I could just use the fence directly really here. And use result. What is the fence used for? Fence is part of the synchronization objects, and I'm gonna explain in a second. I'm gonna complete this code and then I'm gonna exactly explain how and why. And use results. So for now I think I'm just gonna ignore that result, yeah. And next we need to acquire an image. So device acquire image, acquire next image, yeah. Or is it part of the swap chain maybe? Hold on, let me see. Acquire, yeah, it's part of the swap chain. So acquire next image. We need the timeout, which we're basically gonna set as in 64 max, and then a semaphore, which we're not using any semaphores, and of course we're using a fence there. And this returns a pair of results. It returns a result, which I'm not gonna care about right now, and then a UN32T, which I need here. Though for the UN32T I need it, I'm gonna store it. So it's gonna be like a UN32T image index. The current image index, current swap chain image index. Well, actually, what the heck? Current swap chain image index. There you go. And now here, what we're gonna do? Current, or should I say just image index, basically. And there you go. Let's just call this acquire result, because we already used this thing right here. And yeah, that's basically it. Now we do have to handle these results later on, but for now I'm just gonna ignore them. So swap chain image, current swap chain image index is equal to image index, and there you go. Next, we're gonna present this image. VkQ present. We're gonna use our graphics queue, I think, and then we're gonna need the present info. I'm gonna explain all this in a second, just hold on. Semaphores, we're gonna go with fences. Well, apparently we're gonna need semaphores anyway, yeah. Isn't it? Yeah, we're gonna need semaphores anyways, I think. So let's go ahead and add them too. Fine. CD vector. well, render finished semaphores and image available semaphores. Well, also we could use these first, that, and also we could do both like this. And let's actually go to init sync objects and make use of that. So vkSemaphore, create info, semaphore create info, in place back, in place back. So we're creating basically multiple semaphores here. And then let's go back. .sit, well, in fact, before this stuff, let's just go straight into resetting the command buffer. So command buffers .reset with the flags. Do we really need any flags here? I don't think so. Not really. Not really, yeah, no need. So we're just gonna say that. Though for the command buffer, we're just gonna hold, well, a reference command buffer like that. And now we could just use it directly. Reset, and then we're gonna need to start recording it. So begin info. Yeah, we're gonna need vk command buffer begin info, begin info dot. What we need here. So there's flags, inheritance info. I think we're only gonna need flags here, one time submit, and then we could basically use it to begin recording into the command buffer. And then we're basically gonna stop recording, end the recording. And then we're gonna need to submit that command buffer to the GPU so we can execute it. So how are we gonna do that? Graphics queue, do submit. And here we're gonna need an array of submits. So cd array submits. Hold on, submit. Yeah, we're gonna need submit info first. My bet. So vk submit info. Submit info. Let's see what we got here. So command buffers. Let's actually set command buffers. And we're just gonna give it our command buffers, I think, no? No, it's, I see. Okay. Can we just do that then? Alright. Submit info dot. Yeah, wait semaphores and signal semaphores. So basically this acquire next image would signal the image available semaphore when it's ready. Image available semaphores. and then this guy would need to wait for that to happen. Actually, it needs to wait for the rendering to happen, yeah, but right here we have no rendering basically, so yeah, so let's just set wait semaphores and let's just use that anyways for now and see how it goes. And then we're gonna, once we're done, we're gonna set signal semaphores. Oh, actually, yeah, that's correct. I see. Render finished semaphores. Is there anything else that we need here? Let's see. Yeah, one last thing is the wait DST stage mask here. So VK pipeline stage flags. Right here, I'm actually gonna do transfer. Oh boy. Can be made const expr. Okay, sure. And I think that's basically it. Now we could just give it the submit info and defense. And we're done. After that, we could just get the present info, set the image indices, set the swap chains, set the wait semaphores to render finished semaphores, and then present. Of course, this gives us another result, so I'm just gonna ignore it again for now. And finally, we're gonna wait for the fence. VK. Actually, we're already waiting there, yeah. We're waiting at the start here. Currently, the command buffer is empty. We need to add something to it. But let's see if this works first of all. I do expect some validation errors because the command buffer is still empty. But apparently we already have some errors here. So yeah. Now the one thing about these constructors like that and all those implicit conversions is these errors. Cannot convert from VkRAII command buffer to T, where T is const vk command buffer. Okay, so the thing is where this is exactly happening. So basically somewhere I'm passing a command buffer RAII instead of passing a regular command buffer. That's what's happening here. And probably that's the case here. So let me just do that, and it should give it the raw handle instead. Same thing with the semaphore. Instead of RAI, I need to give it the regular one somewhere. So here probably, I guess. Probably same thing here too. Probably same thing here too. That's what I hate about implicit conversions. It makes things convenient, but swap chain, same shit, I guess. But where exactly is that swap chain having problems? No, this one actually, it is, what? So it is expecting, cannot convert from TY, from this to const this. Yeah, actually we need it twice. Once for the optional and second for the raw type. Yeah. And finally we solved the compiles errors, but it seems like it's frozen for whatever reason. Interestingly. Yeah. Shouldn't the signal come after submission? Let me see. Present KHR. Oh, hold on, my bad. So we need to wait first, then reset. My bad. You are basically waiting indefinitely there because we were setting it first and then trying to wait on it. Let's see now. Alright, we're up and running right now. We're just having some validation errors, which are to be expected. Is already in use by another submission. Alright, so I think we're probably fine right now. We just need to complete the actual command buffers. Okay, so let me actually try to explain this mess so far. There's a lot going on here. Synchronization is kind of a rough place when it comes to Vulkan, but hopefully I'm gonna try my best here. Right, so the first thing first that you need to notice is that these fences are made signaled. So if we go to the init sync objects here, they're signaled by default. Right? When we create them signaled. Now what are these fences and semaphores? They're sync objects. Fences are used to basically synchronize between the GPU and the CPU, while the semaphores are used to synchronize the tasks in the GPU itself. So GPU to GPU operations. What I mean by this is that anything we actually put into this command buffer, which is basically a to-do list that we give to the GPU, and even outside of the command buffer, the other commands like acquire next image, present KHR image, etc., etc. All of these commands, like Vulkan doesn't assume any order about them. Like it's just total chaos. How you actually tell Vulkan which order these should happen is using these synchronization objects, using semaphores and fences. Now let's see what's going on here. The first thing first is that we're waiting for the fence. Now at the first frame, this would just like it doesn't even exist because the fence is started to be signaled by default. So we have no problem here. And then we reset the fence, which means it's back to its in-signaled state. So we could actually reuse it again. Right? Now, this is where the magic starts to happen. This is where we start a real frame. So we try to acquire an image from the swap chain. Again, a swap chain is basically just a collection of images, off-screen images that we use. Right, so here the timeout, how much time we could wait for it. Here we're just saying, you know, whatever, infinite. And here we're giving it a semaphore, basically, which is called an image available semaphore. I call it that. So basically when the the swap chain gives us an image, it's actually going to signal the semaphore. It's like a, you know, feu rouge. Like red light, right? It's going to give the red light for whatever other operations that are waiting on this image available semaphore. And we're also going to signal the fence when that happens. The fence that we actually use to wait for here, as you can see. So that's cool. And here we also get the image index. Now the image index is basically the index of the image that we acquired from the swap chain. So yeah, Now next up, what we do is we reset the command buffer so we could record again, because we're using the same command buffer for every single frame. Right here, we're actually trying to begin that command buffer, and we're saying one time submit because we're submitted once and then we're going to reset it in the next frame again. Here we're beginning the recording of the command buffer. Now here's supposed to be commands to record the commands to submit to the GPU. We're not doing this just yet, which is the thing that we're going to do next. I'm just trying to explain this first and then we end it. So once we're done recording the command buffer in the CPU here, we need to submit it to the GPU. So like a command buffer is like a to-do list that we're going to submit to the GPU here. So submit info, and basically we're going to use our graphics queue to submit that command buffer that we recorded. And also we're going to give it a fence here. And hold on a second. Submit fence. Once it's done, it's basically gonna signal that fence, huh? But no, what? Actually, this should be off. Hold on, my bad. This should be null PTR, I think. So we're not gonna signal any fence here, but here, once this command buffer like complete execution in the GPU, it's gonna signal this fence. And so why we want to signal this fence, so we could actually give the signal to the CPU to start the next frame. It is safe for it to start the next frame. Otherwise, don't. It's just gonna wait there until the GPU is done with the frame resources, basically. Okay, what's next? So as you can see in the submit info, this is the command buffers that we're gonna submit. And here we're setting which semaphores we should wait before starting the execution of this command buffer in the GPU. As you can see here, we're waiting for the image available semaphore, which is signaled by this acquire next image, which means that this submission of this command buffer would only start until the acquiring of the next image from the swap chain, which is great. The next thing is set signal semaphore. After the execution of this command buffer is done, it's going to signal a render finished semaphore here, as you can see, which we're going to use later for another GPU operation here. So yeah, and for the wait DST stage mask, this is irrelevant for now, just ignore it. I'm going to explain it later once we get into the recording of the commands here. The next thing is presenting the image from the swap chain to the screen, right? What we need here is to set the swap chain that we want to present, as you can see, set the image indices, which image in the swap chain we want to present, and then set the wait semaphores. We're only going to present until the render finished semaphore is done, which is signaled by this, which means that presenting would only happen after this command buffer finish executing. So hopefully this makes sense. It's kind of hard to understand at first, but this is basically kind of the thing. So like the presentation is waiting on the command buffer to finish executing, but the command buffer the command buffer is waiting for the image available semaphore. I'm assuming the graphics queue submission will actually perform the render, so doesn't it make sense to signal the render finished semaphore after the submit? The signal, yeah, it is render finished semaphore. Hold on, we are signaling that. Yeah, there we go. We are signaling the render finished semaphore after the command buffer execution is done, which would actually do the rendering part. And here the presentation is waiting for that semaphore to finish. Then it's going to present to the screen. After that, here we're going to wait until the GPU is done with the frame. Because, well, this fence is actually, yeah, so like when the render is done, this fence would also be signaled. And the difference between the fence and the semaphore is that the fence, we could actually wait on it from the CPU. So as you can see, device, wait for fences, fence. So yeah, hopefully this makes sense. Now let's get into the actual commands that we're gonna execute in the GPU here. Now for now, usually other tutorials, what they would do, they would already make a pipeline and render path and all that crap, which would even confuse you even more than this. But for me, I'm just gonna go with simple transfer operation. Not really a graphics operation, which is basically clearing an image. So we already have the swapchain image, we could clear it to a color using transfer operation. So how we do that, command buffer dot clear color image, and here we just give it the image that we want to clear. Now here we got the image index of the swapchain, but we don't got the swapchain image. How are we gonna get that? Well, it's actually very simple. So autoconst swapchain image is swapchain images that we got from the swapchain indexed by the image index we got here, which is great. By the way, one thing that you need to make sure to understand is the fact that all these functions exit immediately. Like they don't yield, they don't, like for example this acquire next image, it would return immediately with the image index. It's not gonna wait until the acquiring of the image happens. It's just gonna give me the image index that would be acquired in the future. And when that future would happen, it would actually signal this semaphore. So everything right here is like happening asynchronously from the GPU. So we're kind of like just recording commands and recording dependencies. The only yielding function here is wait for fences. This is where the actual waiting happens. We're waiting for the GPU to finish the execution of this command buffer right here. But yeah, so because otherwise what we're gonna happen is that we're gonna step on the toes of the CPU, right? So the CPU would start corrupting our command buffer and all the other resources that are actually being used right now by the GPU, which is a violation of the API. But yeah, whatever. Clear color image, swapchain image. Let's see if this works. How would this work for the very first submission where there are no dependencies? What do you mean by no dependencies exactly? The fence actually starts in the signaled state. So in the first frame, it's like nothing, you know, it just would return immediately. There's no waiting happening here. Because in the first frame, the fence starts as signaled state, if that's what you're asking about. So yeah, let's see what we got here. Makes sense. All right, cool. So now we have only one command, which is clear color image command. This is a transfer command. It's just a memory operation in the GPU. So here we're telling the GPU, we're instructing the GPU to execute a command, which is to clear this swapchain image. And here, what are the arguments? So image layout, I think this is the image layout, the current image layout of the image, because Vulkan doesn't actually, the Vulkan driver doesn't keep track of the resources, layouts, and state essentially. So every single thing, you gotta tell it yourself what is its state currently. Here, clear color value, which is just empty, which is gonna basically be black right now, and vkImage subresource range, though we do want some more interesting color like red, so we could actually see if this really works, because it is by default already black without any rendering. So yeah, vk clear color value color. All right, so this is RGBA values. Let's just go with 1 here for that red, so it's going to be a red color. Okay, at const, make const exper, perfect. It's gonna start as an indefined image layout. Yeah, it should work. Let's see. There is gonna be some validation layer errors, but maybe it would work anyways, although not perfectly. But we're gonna fix those in a second. And there you go. We finally got a red window, which is perfect. But let's fix these validation problems, why they're here. I guess maybe let's have a look what's going on here. So VUID, vkCmdClearColorImage, image layout. So it's talking about, well, actually here's a little thing that we could also do here is we could check this break here in the validation layer, and when we debug this, it would actually break on that error, right? And then I could go back in the call stack here and see what's going on. So the error actually is happening here. This error is happening right here in this call stack or this call site. So vkCmdClearColorImage, which is correct, yeah. But where it's in the image layout, it's talking about the image. There's a problem with the image layout here, apparently. It's also giving the information, the addresses and stuff. So p range is 0. Layout for cleared image is vk image layout and defined. So it's telling us that the image here, the swapchain image, is in the layout in defined, but can only be transferred DST optimal, shared, present KHR, or general. So for a clear color image operation, it should be transfer DST optimal layout, not in defined. So let's actually try to do that. Let's use that instead. So E transfer DST optimal. Why we actually do need this? We need this because this clear color image is a transfer command. It's a memory transfer command, right? So the best way to actually draw into this image, or like to use this image with this command, is this layout. How can I explain this? So there's multiple layouts of images. There's even general, like if you really don't know anything about those, there's general, you could use it, but it's less performant because like the images are implemented in multiple layouts which are efficient for different operations. So like the layout that is optimal for transfer commands isn't the same layout as that is optimal for other commands like graphics, let's say, or whichever. But yeah, let's see now what other errors we're gonna have next. And fix one by one. I mean, I already know how to fix all of these errors in one shot, but in fact, knowing how to debug these errors is way more important than me telling you how it works directly. So what's going on here? vkCmdClearColorImage. Where is this happening exactly first? Here. The same function. So it says that the image was created with usage vkImage usage transfer src bit and color attachment bit. So it's telling me that it's missing this vkImage usage transfer DST bit. Now this swapchain image, where it's actually created, it's not created by us. It's created by the swapchain, the WSI, which is like the OS, the operating system. But we do actually control that layout. If we go back to initializing or recreating the swapchain function here, image usage here, we said only eColor attachment, but in this case we also need, for the transfer operation, we also need that transfer DST. There we go. So we could actually use that operation on it efficiently. Now let's see what's gonna happen. It should fix this problem. So basically I'm adding another image usage flag there. Alright, what's next now? Now we're actually finally having the error in another place in the submit function here. Okay, what's going on? So the command buffer expects vkImage to be in layout, vkImage layout DST optimal. Instead, current layout is in defined. So basically it's telling us that it is expecting the swapchain image to be in this layout, DST optimal, because, well, we are trying to use it in this layout, but it's actually in defined. So we need to actually transition the image layout to transfer DST optimal. And how we do that is using a pipeline thing. What is it called? A pipeline barrier, okay? So we use pipeline barriers to transition image layouts and to do all sorts of other stuff, basically. So we need right here to transfer image layout to transfer destination using a pipeline barrier, image memory barrier. There we go. Okay, there's all sorts of crazier stuff here that I need to explain. It's actually quite complicated, but let's see. Can try my best. Let's see. So the SRC axis mask, is this correct? It's not really correct, but I'm gonna keep it like that for now, so I could show you another error. And here, transfer right. So here we're basically transferring the image axis mask. We're telling Vulkan that we want to actually next to write to this image, because this, well, sorry, this clear color image actually writes data to this image. So we do need the write axis here, the transfer write. Write because we're gonna write to it, and transfer because this is a transfer command. For the SRC axis mask, since we're just starting in the frame, we don't actually have a source axis mask, though as we're gonna see in a second, this is actually wrong. But for now, this is okay. For the old layout, of course, the old layout of the image is undefined, but the new layout that we want to transition to is transfer the DST optimal. So it would become optimal for this command right here. And next, which image we want to transition is the swapchain image, and the sub-resource range. You don't have to worry about this for now. This is basically used to select a subset of the image, but for now you don't really have to care that much about this. Just hard code it like that. The pipeline barrier. Now here we got a pipeline barrier, which gonna use this barrier struct here. So we're transitioning from the stage transfer to stage transfer. You don't have to worry that much about that right now, but basically there's multiple stages in the GPU that can actually happen simultaneously. Like you could have the GPU doing transfer operations, uploading textures from the system memory, while actually also doing graphics operations in the at the same time. So we actually use this pipeline barriers to actually, you know, wait for stuff to happen before we do other stuff. Here we're waiting for any transfer operation to happen before we do any other transfer operations. And yeah, and then we just do that. All right, cool. Let's see what's gonna happen here. In fact, let's just say etop of pipe, because this is what's like obvious here, because we have no other operation beforehand, so we don't need to synchronize anything here. But we're gonna have an error about that in a second. The other thing that we're gonna need is to transition the image layout again from transfer the DST optimal to presentation, to present the image. And for presenting the image, it's going to read the image, which is going to be transferred SRC optimal. Though yeah, presenting an image is also transfer operation, but not destination, it's source. So what we're going to do is just to simply copy this whole thing, this pipeline barrier. After the clear color image, I need to transition the image again. So the previous stage that we had is a transfer operation, and the next one is, we could just say bottom of pipe for now. This is wrong actually, but I'm gonna fix it in a second with another error. But concept error has already been defined or declared. Yeah, I guess we'll call it barrier 2 then. So here, what is the previous access flags? The previous access flags is transfer right. So this is the SRC access mask. The new access mask is presentation, which is reading the image. So this is going to be a transfer read, right? And so the new layout is transfer SRC optimal. The old layout is not defined. The old layout in this case is this guy right here. Transfer the ST optimal. And there we go. So this should do the trick. We do have one little small problem left, but let's see first what's gonna happen with this one and see what's the error. So we have a problem in CMD pipeline barrier. DST access mask is not supported by stage mask, stage of bottom of pipe bit transfer read. Oh. Okay, which function exactly? This one. Ah, I can't use bottom of pipe then. Interesting. Interesting. Well, let's just go with transfer anyways. And honestly here, let me see if I can get the error. I really want to explain that. Hold on. Come on. How much time? 3 hours. Okay, interesting. Oh, sorry, not transfer SRC. My bad. Present SRC. Yeah. So where's that thing? Hold on. Not SRC. Present SRC KHR. Okay. My bad. The other ones should probably be fine, I guess. Because it's source of presentation. And no validation. Well, actually there is one more. Yeah, so here when we try to destroy the fence, it said that it cannot be called on vkFence that is currently in use. So we cannot destroy it while it's still in use by the GPU and such. To fix that is, before we actually destroy the application, we need to make sure to wait for the device to finish execution of everything. So what we could do is to simply wait idle. Wait until the GPU is idle. And then destroy everything. And now we have no errors anymore, no validation errors. Perfect, so we have solved all of it. But there is still though a problem here. It's just that it didn't tell it in the validation layer for whatever reason. Maybe it would in the synchronization part. Synchronization layer. Let me see. Yeah, there you go. Sync hazard right after read. But can it actually break into the function call? Hold on. break. There we go. Let's actually make a break. All right, there we go. So here we have a hazard right after read. Right after read. Where exactly? Oops, hold on. Let me actually grab the... So we have it here in the submit function. Unfortunately, it doesn't tell us exactly which one, but anyways. But basically, this hazard right after read, meaning that right after read, we're writing straight after read without like synchronizing well. And why that's basically happening is because here we're assuming that like at the start of the command buffer, the actual image is in a good state, but it's not. It's like when we start a second frame, the image is still being read by the previous frame. So what we should make sure here in access flags is not nothing. It's actually e-transfer read. Access flag bits e-transfer read. What about now? So like you're not just synchronizing the commands that is inside of the command buffer of this frame only, but also the previous frame and the next frame too. And what the heck is going on here now? Let me make sure that I have all my stuff good. So transfer read, transfer write. Actually, not even transfer. We could even say memory read, really. And probably here too, memory read for the presentation. Notice that the DST here is the same as the SRC in the start of the command buffer. So it's kind of like looping. Hopefully this would fix it. Let's see. Oh boy. Did I miss something else? Hold on. Okay, how about the... Wait, stages e-transfer. This seems about right, actually. Oh, my bad. Here, top of pipe. Instead of top of pipe, we also want transfer here. And let's see now if that fixes it. All of them are transfer because we only have transfer operations, so there's no need to like synchronize the other operations. Later on, we're gonna also have graphics, which is gonna be crazier. But right now, we're good. And finally, we have no synchronization problems and no validation problems either. Which means we're finally have made a fully functioning airless Vulkan window. Synchronization is perfect. Everything is perfect. But yeah, it took like around 3 hours to explain all that. Is there any questions so far? Is there any that's a lot of crap, and I do recommend some other resources too, which I think I'm gonna put in the description. I'm gonna update the description of this live stream to put those resources. Other than that, yeah. One last thing that we can do is, instead of having one like constant clear color, we could have like an animating clear color. So here's the deal. Could have auto ticks, SDL get ticks 64, I think, or yeah, get ticks. And this, is this code available in a repo? Welcome to the live stream. It's gonna be, yeah, it's gonna be, I'm gonna make it available after this live stream. I'm gonna put it down in the description or the comment section. But yeah, so auto ticks is the get ticks. So this is UN64. We need to put it into, convert it into F64, I think. Double, yeah. So static cast double welcome double, and then times 0.01. Because this is in milliseconds, we turn it into seconds. And now we could actually use a sine wave. So instead of one constant, we're gonna say std sine of ticks times 0.5 plus 0.5, because, well, the sine wave actually goes from -1 to 1. I mean, if you go to Desmos here real quick, just for the sake of completeness, this is a very useful tool for mathematics, for graphing. So sine wave goes from -1 to 1. We need to make it go from 0 to 1, because that's the range of the color. So how are we going to do it? The first problem that we have is that this actually have the size of 2, because it goes from -1 to 1. So we need to do times 0.5, so it becomes, it would have a magnitude of 1, right? So right now the distance here is just 1. But more than that, we need to actually take this graph and take it up by 0.5. So we're going to say plus 0.5. To actually make this even more clear, what I could do is this. Whoops, not that. Let's just say 0 here and A here. Yeah. Look at that. So I could actually use that to take the graph up and down, right? But like you could just say 0.5 and there we go. That's that. And this one we could say B. But yeah, to make it from 0 to 1, we need 0.5. Yeah. Other than that, let's see what's gonna happen here. Times 0.5 plus 0.5. But it doesn't accept it because I guess it's double and it should be a float in this case. Okay, let's see if this works. Oh yeah, it's no longer a constant, apparently. Well, at least not a const expr, but yeah, because it's relying on the ticks, which is a runtime value. Or honestly, instead of ticks, I should call it T for time, because it's actually time in seconds, not ticks anymore. And it is working, as you can see, but it's quite slow actually. We could speed it up a bit. And how we could change, like we could speed it up a bit by scaling the x value by a factor. Oops, not A. Let's see something like C, for example. And like if we could increase the frequency of the sine wave, so it's going to become faster oscillating. So how are we going to do that? Well, we could do it here. And also instead of ticks, let's call this T for time. And there you go. We could here, for example, I basically times 2 means it's going to be twice as fast, because like twice as much as the frequency, right? Not fast enough still. What about 5 times? Come on. And there you go. That's much nicer. So there you go. We can have the red color up and down. To top it all off for today's video, I think I'm going to show you a bit of RenderDoc 2, which is a debugging application. So we could end this application. And of course, in the next stream, we're going to go into a more advanced example, which is basically loading a texture using SDL image. And yeah, goodbye loop preliminary. I'm just going to cover one more thing, and then we're going to end the stream. So as I said, in the next stream, what I'm going to do, I'm going to cover how to load textures using SDL image, and then basically transfer them to the VRAM of like the video memory of the GPU to the VRAM, and then basically take that and bleed it into the screen or the window using a transfer command. We're not going to do graphics just yet. And yeah, that's all it's going to be about. After that, the stream after it, we're going to actually get into some graphics stuff. Graphics pipeline and stuff like that. Because like in this stream and the next one, you're going to be quite decent in like synchronization and memory operations, right? So I didn't want to basically make it even harder with graphics too. I wanted to have some foundation first and stepping stones, and even visual stepping stones. You can actually see something into the screen faster. I mean, so far we got 279 lines of code. An actual triangle without the RAI and stuff, that would be way more. But yeah. Other than that, let's actually try RenderDoc as the last thing here. Let's see, copy path, absolute path, executable path. So I just copied that path and launch. Allow. Okay, so I have a little problem here. I did get this error before, I just don't remember exactly how I fixed it. Oh yeah, I see why. So this is something to look out for. When you actually want to use RenderDoc, make sure to disable the Vulkan validation layers. Otherwise it wouldn't work. And there we go. So as you can see, I'm getting right now 2500 FPS. Though, like without RenderDoc and without me actually streaming, this would have been 7000 FPS on my GPU, on my system. But yeah, I could also right now print PRT screen to capture a frame. So here, as you can see, I captured this frame right here, and then I could quit. And now I load this frame and see what the heck is going on. So as you can see, it's a BGRA8 image, sRGB. And this is the color, as you can see. It's 800 by 600, 1 MIP maps. And it's called swapchain image 143. There you go. I could right click pixel here, as you can see and stuff. And I can see the inputs, which is nothing here. We only have one output, which is the actual swapchain image basically right now. This would be more complicated later on, but yeah, you got the point. So here we got, this is the frame, capture start. We got one command, which is a vkCmdSubmit. And before this vkCmdSubmit, we had a wait for fences, then a reset fences, then a qsubmit. And this is the device, the fences, etc., the timeout, wait all, qsubmit here, the submit, as you can see, p-wait semaphores, DST state. So we could basically see all the commands that are running here, as you can see, and basically debug them. So that's pretty sick. vkCmdClearColorImage, image layout, colors, as you can see. But yeah. So I guess that was it for this stream. Thank you all for coming in. I don't think you would find any better tutorial than this if you can go through all the 3 hours. But yeah, that was it guys for this stream. Thank you all for coming in, and see you later. Goodbye everyone.